Okay, good afternoon, everyone. Welcome to our presentation. Today we're going to be talking about composite video device abstraction for Libcamera. My name is Karthik Poduval, and this is my colleague.
My name is Kamal. Yeah.
Right. So is this talk is about kind of like a software design that we did for Libcamera. So we'll start with the problem statement as to why we designed something like that, and then what were the other design choices, and start explaining more about this design. So let's first start with an ISP, a complex ISP. So this is a typical ISP. You'd have an image sensor on the far left here. Let me use a laser pointer. So it's an image sensor, and that interfaces with the ISP for data pass through maybe CSI2, for example, and the control for the control pass it would be I2C through an I2C controller. So you turn on the image sensor, apply settings and things like that using I2C. I also do some dynamic setting changes while it's running using I2C, and all the image data would transmit to the SoC via CSI2. So inside the SoC, there's going to be a CSI2, which is coupled with the D5, which is the PHY for the CSI2 protocol, and that will decode the frames and convert it into a format that the rest of the ISP can consume, right? And in this particular ISP, we are showing a few stages of processing, like black level correction, defective pixel correction. From here, there is a fork that goes towards generating statistics. So statistics, image statistics like histogram or counting statistics are used by a collection of algorithms known as 3A. It stands for autofocus, auto white balance, and auto exposure. And these statistics are produced on a per frame basis usually, and they'll almost usually have a DMA so that they're made available per stream. So there are some statistics engines that might write out to registers, so those variants also exist. And there's another fork that continues down the pipeline to do a demosaic. Basically, that stage is going to change a raw bare format. That's typically how the sensors produce their image, which comprises of a BGR, but in a bare pattern arrangement, and that arrangement has twice the number of green pixels as compared to red and green, because it's been shown that human vision is more receptive to collecting more green light. So that's the theory behind it. And so this needs to get changed into RGB or YUV formats. And the demosaic block, its job is to produce an RG and a B value for every pixel, because in the bare format, a given pixel is either R, G, or a B. So this is like a mosaic, in some sense. So the demosaic block is going to interpolate and come up with red, green, and blue for every pixel. So that is a very necessary and important step in an ISP. After that, there could be other blocks, which it could be in the domain of color correction. You could even have an optional color space conversion along with scaling, downscaling, upscaling. This is typical, right? You'd have a very high megapixel camera, and then you need a downscale preview for one stream and another stream for the full resolution camera capture so that you can save a JPEG. So this is a very typical ISP, and at the end, right, these two blocks, the scaling and color space conversions, will also have DMAs associated with it that'll allow you to save a downscaled preview, for example, and a full resolution JPEG, or even the JPEG could be downscaled, right? Depends on the use case. After this, there are other processing blocks that may follow, which are not necessarily inline like shown over here, right? But they might be memory to memory in nature. So two examples shown here are, one is a dewarp. So the dewarp is a block that will it will remove the warping effects that lenses introduce on cameras. So all cameras have lenses, and due to the nature of the lenses, everything that it captured is warped by nature. So straight lines will look warped. And the function of the dewarp block is to straighten that and remove those imperfections and produce an image in which a straight line, like a pole or something, straight. So that's one of a very often used post-processing block in a camera ISP pipeline. And then if you were to save this image as a JPEG, which is what happens in our smartphones, right? So you need a JPEG encoder for those use cases. So these are memory-to-memory blocks, meaning typically because they can't work with line buffers necessarily. They need a much larger line buffer count. So it makes sense to make them as memory-to-memory block. So the output of the first stage, the inline stage of the ISP, those buffers would be read line, and then they would be dewarped in a memory-to-memory fashion, and optionally also sent to a JPEG encoder. So this is kind of the hardware we are dealing with here in general. Most ISPs will have some version of this, may have additional post-processors. Some blocks might be done in post-processing, but it's a very typical representation of an ISP. So now, how to represent this ISP in Linux camera stack, right? So the default Linux camera stack for ISP is V4L2 along with media controller. So what media controller does, it's an extension to V4L2 that allows representation of blocks of an ISP, logical blocks, as a media graph, which can be seen in the first diagram here. So based on the hardware architecture we discussed in the previous slide, you have an image sensor that passes through a CSI2 decoder. The PHY is included inside this block. And once the frame is decoded by the CSI decoder, it goes into a generic ISP block, which contains all the blocks that we saw here, right? All of these put together. And there'll be various V4L controls that you can apply onto this video subdev device to control the ISP in real time. And the output of this ISP is two scalar outputs, which actually includes scalar and color space conversion, and a statistics block, which is used by the 3A algorithms, like I mentioned earlier, right? So this is one part of the pipeline, which is the inline part of it, you can say, which is a ISP media graph. There are two additional media graphs which represent the memory-to-memory devices we spoke about. So that's shown here. So there will be a dewarp source, dewarp proc, dewarp sync, and similarly JPEG encoder source, JPEG encoder processing, and JPEG encoder sync, right? And they are individual video devices. So these are multi-context by nature, meaning that you can open them multiple times, and every time you open them, you get a specific context. So that makes it possible to use these for, like for example, let's just say all of our streams, there are only two streams in this camera. They need to produce, go through dewarp, post-processing, as well as JPEG encoding. So we could do that with two instances of dewarp by opening the video 3 device node twice. And same goes for the JPEG encoder. You open the video device twice. And those contexts, one of them can operate on scalar 0, and the other can operate on scalar 1. So now my colleague will talk about how to deal with this complexity in Libcamera.
Yeah. So back in the days when the camera is a simple V4L2 device, right? So we don't need to manage this many complex nodes. For example, as shown in the diagram, there were so many nodes connected here, right? From the CSI to generic ISP to scalars, and then the post-process like a dewarp and JPEG. So we don't need to deal with this many node topology. So it's as simple as just you configure and you get the image streaming and all. But now, because of this complexity, we need to use multiple APIs to build our pipeline. For example, how to go through all of these nodes and how to get the desired data out from the ISP. So that's itself, making such kind of a pipeline is a daunting task. So it takes so much time to develop. But all of this complexity can be abstracted by Libcamera. So the Libcamera is introduced in 2019 in the same Embedded Linux conference. So where we have ability to simplify these complex nodes and concentrate on the application more. So for example, as shown in the picture, so we have a pipeline handler, and also we have a image processing algorithm part where we can have our own 3A algorithms and where we can implement our own pipeline handler to handle all these media nodes. For example, on top of that, the Libcamera also supports the camera manager. For example, we can have multiple cameras, like more than one camera. So the Libcamera can manage and abstract all those cameras, but at any point of time, it can operate on the single camera. And also it has several support classes to support the buffer allocations and then maintaining the media devices and all. So with that, we can construct our own pipeline for the two scalars and the post-processors, what is shown in the media graph. So our pipeline consists of a ISP media device and a DVAR post-processor and a JPEG post-processor by using the Libcamera framework. So from the application point of view, it's a two-stream camera, and each stream is capable of RGB88 format, that is the native from the ISP. And our considerations here are, we can optionally dewarp any of these stream, and also we can send to JPEG for encoding. So this is all based on some conditions, right? For example, if user decides to set the format as a JPEG, then we must encode using the JPEG encoder. But the DVAR can be selectively selected by a static policy. For example, based on some resolution, I can imagine that, okay, this stream need to go through the DVARP. So,
cool, thanks Kamal. So continuing further, so now let's, given that we need to implement a pipeline handler for this complex ISP graph, so what are the implementation choices, right? So one thing is that our requirements is that our pipeline handler should be able to handle all these three media devices, which are like the ISP, the DVAR, and the JPEG encoder, right? It kind of needs to decide how to pass frame to DVAR, right? This could be based on a static policy like Kamal described. And the decision to pass to for JPEG encoding depends on the application. If the application requests a JPEG stream, then you would generally pass it for JPEG encoding at that point, right? So that's sort of the requirement now. Now the simple way to do it would be to actually handle all of this inside the pipeline handler, but we thought there's a better way, and that's sort of what we came up with. It's known as what if we did a composite video device abstraction, which means that the pipeline handler is going to encapsulate all these three, not pipeline handler, this composite video device abstraction is going to combine this functionality and then make it look like a single video device, right? So let's talk about the requirements, right? So it must have all the capabilities of a video device, because that's what it's going to look like to a pipeline handler that would be dealing with a similar ISP but without the post-processors, right? So we're trying to make the pipeline handler's code a bit simpler. And it should be able to also handle complications like, intermediate buffer allocation. So because when you are moving from one video device and passing to two different post-processors, your application is just going to give you buffers for the end of the pipeline, right? So all of that intermediate buffer allocation needs to get handled here. You need to be able to set and get formats, and you should be able to redirect it to the correct device, right? Based on dynamically, right? It depends on what the application wants. Same thing for controls, like there could be various controls going to ISP, some could be going to the post-processors. All that needs to get handled. And you need to finally be able to orchestrate all of these callbacks, and it should completely be flexible, also use cases supported, based on how the application decides to use the camera. So these are sort of the high-level requirements. So that's where the composite video device abstraction comes into place. Instead of manually controlling the callbacks between video device and post-processors, how about building a composite video device abstraction? So this is going to be a combination of a V4L2 video device. This is a class in Libcamera that's used to control a V4L2 video device, and V4L2 mem-to-mem based post-processors. And this all functionality gets abstracted now to a single class called Composite V4L2 video device. So this is a C++ class, and it uses standard inheritance techniques to provide this abstraction, right? The convenience class makes the pipeline handler code simplified, because now even if you could go and add more post processors along the way, and your pipeline handler code stays simple because you moved all of the complexity into the abstract class called Composite V4L2 video device. So that was our motivation for going ahead with this design. So let's take a look at the class inheritance diagram. So at the base, we have a V4L2 device, which has a bunch of different utilities to handle a regular V4L2 device, which may be a video device or a sub device. And the V4L2 video device is actually a derived class from that. Up till this point, it's all Libcamera standard. This is a part of the Libcamera library. What we have added is a composite V4L2 video device. So that's basically going to contain, it's also going to have a reference to two V4L2 mem-to-mem video devices for the post processors. And there's an extra variable inside this class, which is known as the composite device use case. So in order to handle the complexity, we thought it's a good way to do it is to have this enum here, which represents the use case. So there are 4 use cases for this particular pipeline. One is video only. That means that anything that the application is requesting is satisfiable by the inline pipeline part of it. So it's just the video device node alone. Video dewarp means output from the video device is going to go through dewarp for dewarp post-processing. Video JPEG means the output of the video will go to JPEG for post-processing. And video dewarp and JPEG means it would go through both the post-processors. So we will see how these use cases get dynamically selected based on how the application is using, configuring the pipeline. So all the methods from V4L2 video device are supported and overridden on a need basis. And all actions taken based on that use case, I was just describing in the last frame. So there's a use case enum class variable that does it. So the dewarp use case gets set based on, there's a static policy for dewarp because there's no good way of telling you need dewarp or not. There's some applications that may not want dewarp, right? So that's why we'd like to keep it flexible. So maybe there's like a, environment variable that says that we need dewarp or not. And then JPEG is very simple because if the application requests JPEG, that means you need JPEG post-processing. So in that case, that use case gets selected, right? So now the video device that is at the end of the pipeline, it is going to use the application's imported buffers, which means that if a pipeline is 2 or 3 deep, the intermediate buffers need to be handled by this class, which is also built into the class. Going to the next. So Kamal, you want to continue?
Yeah. Okay. Yeah, now that we have the composite video device class as described here, so how this class will be initialized, or how this class will have its entities, right? So the initial setup is like, because now we have a 2 post processor here, we need a dewarp mem-to-mem device object, and we need a JPEG, the encoded MTM device object here. And then as we derive from the V4L2 video device from the Libcamera, so we have to pass an extra object here, that is the media entity. And then we construct dewarp and JPEG media devices also in the composite video device class. So the media device pointer here, that is shown here, can be the use of the media device here is for the media request. I think we have a talk tomorrow for the media request, I think by Karthik. If you're interested, you can attend the talk. And finally, when we create the instance of the class, and we'll also create the scalars. That's what our ISP 2 streams. And then the initial case will be the video only, because this is pure setup is happening here, and then no use case is selected by this time. So the initial use case for this class will be the video only. And what we are showing in this diagram is, so what are the base stream on or off functions that will be invoked based on the device policy. For example, if it is video only, we don't need to worry about the post processors. We'll simply either do a stream on or stream off based on the use case. But in case of a video dewarp, we also need to take care of the mem-to-mem dewarp output and capture cases too. So similarly for the JPEG, we'll also consider the JPEG output and capture cases. But what if it is a complex case like a video dewarp and JPEG that should happen? So then we have to also take care the base class and the dewarp and the JPEG. So yeah, that's how the stream ons or stream ops are handled in the abstracted class.
Yeah. So yeah, we can see how that simple variable, right, the enum of the use case can help simplify the code. You can remove a lot of, make the decisions a lot easier, right? What we have not shown in the slides is how this use case gets set, because that was a little bit hard to represent. But as and when we are setting different formats, initially it starts with video only, but as we are setting JPEG format, the use case would switch to JPEG, and the inclusion of dewarp or not is based on a static policy, like we said before. So that's one of the ways to do it. You could also make it resolution-based, as Kamal mentioned, right? So that very quickly, as the pipeline gets set up, the use case gets determined. And this slide, we'd like to talk about the intermediate buffer allocation. We'd like to show that, right? So here, there's a sequence diagram, slightly modified sequence diagram. The blue portion of it shows all the different components. So you do have Libcamera. When we say Libcamera here, it actually means the pipeline handler part of it, not that's also implemented by us. And the Libcamera uses a video device, right? And that's the abstraction we are talking about, right? And internally, it includes a dewarp. So mem-to-mem devices will have two sides, right? There'll be a output side and a capture side. This is how v4l to mem-to-mem functions, right? So you submit a job to the output capture queue, and the output queue actually, sorry, not output capture queue. And when the processing is done, the image becomes available in the capture queue, right? And similar representation for JPEG output and JPEG capture, right? So for instance, now over here, these titles here show the use case. So if it's video only, this means the buffer allocation now is coming from the video device, because it's at the end of the pipeline, right? So when you submit a buffer to the video device, whenever buffer becomes available, you just notify the pipeline handler. So that's a simple use case here, right? Now, if you had video plus dewarp, in this case, once the video device produces the buffer, you need to queue that into the dewarp output queue, right? And when the dewarp completes processing, there's going to two callbacks are going to come, right? One is the output buffer complete, which means that it has done consuming the input side of it, right? And then the dewarp capture would have a dewarp receive capture buffer, and this would get queued to the Libcamera pipeline handler, right? So in this particular case, now there's intermediate buffer handling that is handled by this class, and the allocator here is going to be the video buffer pool, right? Let's talk about the most complex use case, the video dewarp and JPEG, right? In this particular case, what happens is the video produced by the video device is going to be sent through two different post processors, the dewarp as well as the JPEG. So in this case, the output of the video device, once the buffer becomes available, is queued to dewarp output. And then when dewarp completes its processing, this output buffer is going to get returned back to the video device that produced it. But the capture buffer produced by the dewarp is now going to go to the JPEG output queue. And once the JPEG completes its processing, it's going to return the output buffer via the output buffer complete callback, the buffer which would go back into the dewarp mem-to-mem device capture queue, right? And the capture queue of the JPEG, its output buffer is going to go back to the Libcamera pipeline, which would go back to the application, right? So in this case, let's look at the intermediate buffer allocation. So the buffer used between the video device and dewarp is allocated by the video buffer, the video device itself. So that we call that the video buffer pool. But the buffer that's being used between the dewarp mem-to-mem and the JPEG mem-to-mem is allocated by the dewarp buffer pool. So that's what is shown over here. So that shows the, so this line over here is shown here, right? And the last one is pretty simple. It's very identical to video dewarp, which is that we do not use dewarp here. Instead, the buffer produced by the video device is directly sent for JPEG post-processing. So output from here goes to JPEG output queue. After the JPEG is done processing, that the output queue's buffer is returned back to the video device, and then the JPEG capture queue buffer is sent back to the application. So yeah, that's, I guess, is the last slide. So we are open to any questions. Sure, yeah. How much time? It depends on various factors. It depends on the design. Like the inline ISP is pretty, I would say, fixed, more or less, based on the clock frequency, right? And it's also timed by the sensor, right? So the sensor will transmit at 30 frames per second. So you're going to get a frame, 30 frames, like one frame every 33 milliseconds for the inline part of the ISP. But the post-processors, since they are mem-to-mem, the amount of time they take, it depends on the size of the buffer. So larger buffers are going to take longer to process. It's true for both DWARP as well as JPEG post-processors. Right.
So the question is that Libcamera here is like, what's the difference between Libcamera here from Amazon camera and Vedantham from like other manufacturers like Canon or Sony or like
What's the difference between various Libcamera pipeline handlers, you're saying, right? So one is that so the Libcamera API is the same for all of them, right? I mean, as such, the API allows you to discover your capabilities. There are APIs built for learning about how many cameras are there on the system. Then you can go to each camera, you can query its static capabilities, its stream capabilities, and Libcamera API will help all the pipeline handlers will advertise that I'm a 2-stream camera and these are all the stream formats supported. They'll also have a list of resolutions that are supported, so you can learn about it, right? So different implementations will advertise their capabilities. So some implementations are single stream, some of them are 2-stream, and there could be multiple streams as well, right? So and the resolution supports and all of these things are advertised via the pipeline handler to Libcamera API, so you can query it. So you basically, but the API is the same. I mean, but you choose it based on the hardware capability actually. So if you need like larger megapixel support, you go pick up an ISP that has a higher megapixel support. So that's sort of how it works. Yeah. Cool. Any other questions from the audience? Cool. In that case, we could end a bit early. Thank you. Thank you so much for being here.
Thank you.